Well, hi there, boys and girls. We're going to take some notes over rational functions here. So we're going to do rational functions. We're going to figure out what they are and how to graph them. So the first thing we're going to do is we're going to define, oh look, that's like magic. I just pressed the button and out come rational function. Is a function whose rule can be written as a ratio of two polynomials. So we're going to have a polynomial divided by a polynomial. They are going to look similar to these graphs that you see here. It's going to be there's several things that we have to do to graph these, but it's actually fairly easy if you know how to find the asymptotes and the x and y intercepts. So just hang with me and I'm going to show you how to do this. Okay, now what we're going to do is we're going to have to find intercepts, asymptotes, and let's talk about what asymptotes are. First of all, a vertical asymptote is a vertical boundary line. It's like in the form x equals, like x equals 2 is a vertical boundary line at 2. This is the only kind of asymptote that cannot be crossed. It is a boundary line as in it's a guiding line, but you will never ever see a graph touch a vertical asymptote. A horizontal asymptote is in the form y equals, and that's a horizontal boundary line, and this is like a limit as we're going out towards infinity or negative infinity, and you can cross horizontal asymptotes. That's okay. An oblique asymptote is sometimes also called a slant asymptote. This is sometimes called a slant asymptote. And that's a diagonal boundary line. And again, it's okay to cross those. We just cannot cross vertical asymptotes. Now, all rational functions have a parent function, and of course that parent function is 1 over x. And if we make this little table of values here, if y equals 1 over x, this table of values would look like this. This one would be really interesting. 1 divided by 0. I'm going to leave that blank because that's undefined. We cannot do that. That's going to be really big because that's where our vertical asymptotes are going to show up. Okay, 1 divided by 1/2 is, of course, 2. 1 divided by 1 is 1. 1 divided by 2 is 1/2. Okay, so we've got some dots there. And our domain is all real numbers. We'll do that little r, except x cannot equal 0. So we can, those which make the denominator or the bottom equal to 0. Alright, so let's take a look at this graph here. We've got these dots from -2 and -1 that looks something like this on this side, down here in quadrant 3, and then up here in quadrant 1 it looks something like this. That's our parent function rational function. A horizontal asymptote is a horizontal boundary. The horizontal boundary here is y equals 0. The vertical asymptote is this vertical boundary, and that is at x equals 0. So you notice the vertical asymptote is in the form x equals, and the horizontal asymptote is in the form y equals. Okay, so what we're going to do first is we're going to talk about vertical asymptotes, because these are probably what I graph first, and we're going to find the value that makes the denominator equal to 0. So let's take a look at a couple of examples here. Here's a function x over x plus 1. What we're going to do is we're going to take the denominator and we're going to set it equal to 0. And that happens when x equals -1. Now, as long as this value does not make the top 0 at the same time, then this is a vertical asymptote. In this second example, I've got x squared minus 1, so we're going to have to factor and set both factors equal to 0. And that will give us x equals -1 and x equals 1. And again, as long as these x values do not make the numerator 0 as well, they are going to be vertical asymptotes. And here's another one I have to factor, x squared minus 3x minus 4. So that's x minus 4 times x plus 1. And you set that equal to 0 and you get x equals 4 and x equals -1. And there's no x value in the top at all, so both of these are going to be vertical asymptotes. My 93-pound baby, big black lab over there, is moaning at me because he's trying to sleep on my couch, and he's frustrated because I'm talking and keeping him up. He likes to sleep over there close to the fire. It's pretty sad. I'll be done in a little bit, Cole, and you can sleep. sad. Okay, now, for horizontal asymptotes, there are three different things to look at. Since we're looking at fractions, you need to look at C. Is the fraction top heavy? If the exponent of the leading coefficient is largest on top, then let's take a look at an example of what I mean by this. Let's say that I have x squared minus 3x plus 5, and then let's talk about x minus 3. So let's take a look at the leading coefficient. That's a 1. What's the exponent on that leading coefficient? That's a squared. Now look at the bottom. The leading coefficient down here is a 1. What's the exponent? That's the 1. This is top heavy. If it's largest on top, then there are no horizontal asymptotes. This graph does not have a horizontal boundary. Okay, now what if they're straight up? What if the degree of the top and the bottom are the same? For example, what if I had x cubed minus 3x squared minus 7 over 4x cubed minus 6x plus 5? If this happens, if the degree of the bottom and the degree of the top match, then there will be a horizontal asymptote, and it will be at the ratio of the leading coefficients. So we are going to have a horizontal boundary here, and it will be at the ratio of the leading coefficients. The leading coefficients are 1 and 4, so this will have a horizontal asymptote at y equals 1/4. Now, if it's bottom heavy, that means if the bottom is bigger than the top, like x plus 3 on top and then x to the 4th minus 6x squared plus 7, this is bottom heavy. If the degree of the bottom is bigger, then there will be a horizontal asymptote, and it will be at y equals 0. Those are your only three rules for that. Okay, so let's take a look at also what we need to know are intercepts. Intercepts are where the graph crosses the x and y axis. Your x-intercepts are where y equals 0. So what you're going to do for your x-intercepts is really you're just going to set your top equal to 0, and you're going to make sure it doesn't make the bottom equal 0 at the same time. So in this example, x squared minus 2x minus 3, I'm going to factor the top, and I'm going to set it equal to 0, and I'm going to get that x equals 3 and x equals -1. You want to make sure that neither one of these x values make the bottom 0, because we can't be 0 at the top and bottom at the same time. That actually is a hole or a removable discontinuity. We'll talk about that more later. But 3 and -1 do not make the denominator 0, so that's your x-intercepts. Now your y-intercept is a little easier. You plug in 0 for x, and that will be your y-intercept. So plugging in 0 for x, let's see what happens here. That's a 3/2. That is your y-intercept. X equals 0, y equals 3/2. So with our horizontal asymptotes, vertical asymptotes, and our intercepts, we're going to be able to draw these graphs pretty easy. So let's take a look at a specific example, see if we can't draw it. I've got x over x squared minus 4. I'm going to go ahead and factor that denominator into a difference of squares. It's x plus 2 times x minus 2. Vertical asymptotes. We need to set the bottom equal to 0. That happens at x equals 2 and x equals -2. Neither one of these values also make the top equal to 0, so what we're going to do is we're going to draw these little dotted lines up and down at those points. This is the first thing I usually do. We're going to graph a vertical asymptote. Then we're going to graph a horizontal asymptote. Now, horizontal asymptote, we had those three rules. Is this top heavy? Are they even? Or is it bottom heavy? This one is bottom heavy because you got an x squared on the bottom. That means y equals 0 is also a guiding line, so a horizontal asymptote. Let's get some x-intercepts. X-intercept, you just basically set the top equal to 0. And make sure it doesn't make the bottom 0 at the same time. So that happens when x equals 0. So that's an x-intercept right here at x equals 0. And y-intercepts are you replace 0 in for x. And what do we get here? We get 0 over -4. We get 0. So that's also a y-intercept. So the only time this graph ever crosses the x-axis is at is at 0, and also the y-axis is 0. So that's the only other point we have. So let's figure out if we can't graph it. we need to know what happens at some of these other points. So let's take a look out here at, say, x equals -1, -2. How about at -3? If x is -3, where is this graph? It only has two choices. It's got a u up like this or u down like this, because it cannot touch that vertical line. So if x is -3, we're just checking. When x is -3, I'm going to have -3 over -3 squared is 9. 9 minus 4 is 5. -3/5. So it's below this asymptote. So I know then that this graph does something like this. And then let's find out what happens in here. What about as x is -1? If x is -1, I'll write it over here, I'm going to have -1 over -3, which is 1/3, which means it's above the x-axis. So you know the graph does something like this. Remember, it cannot cross those asymptotes. Wish that was a little smoother, but so that's that. And then let's check out here at x equals like 3. If x equals 3, then I have 3 over 5, and it's positive, so it's above. So you know this graph does this. And that is our graph. Let's try one more. Okay, vertical asymptote, x equals 1. But does that make the top 0 as well? Let's go ahead and factor that in x plus 3 times x minus 2 over x minus 1. Okay, vertical asymptote, bottom equal to 0, x equals 1. Dotted line. Boop, 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 boop. Boop, 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 boop. Okay, horizontal asymptote. This one is top heavy, so there is none. There is not a horizontal asymptote. Let's check some other points. What about an x-intercept? That we're going to set the top equal to 0. X equals -3, and also x equals 2. 1, 2, 3, and x equals 2. What about a y-intercept? We replace all the x's with zeros, and so you have 0 squared plus 0 minus 6 over 0 minus 1. Those are all zeros go away, and that's 6. So that's way up there. I can't even see it. So that's your y-intercept. So let's see if we can't make this work here. You know what the graph has. There's no horizontal asymptote, and the graph has to approach this point right here. And we've got x plus 3, x minus 2 over x minus 1. Just 1 second here. Okay, sorry, I had to take care of something. Anyway, back up here to full screen. And so what you can see here is we don't have any horizontal asymptotes. And what we're going to find out is that this graph actually has a slant asymptote. And I'm going to show you how to get that in just a second. But what's important is this graph, as it's approaching this vertical asymptote, it's got to go straight up like that. And then from over here, it does this. And I want to show you why I know it does this. And down here, it does something like this. This graph actually has a slant asymptote. I don't want to fill that in because I need to see that y-intercept in just a second. This graph has a slant asymptote. That's also called oblique. Now, how you can get that slant asymptote is actually by dividing this. This will only happen when the numerator is 1 degree bigger than the denominator and there's no horizontal asymptotes. So the way you get this is you come down here and actually do synthetic division. 1, 1, negative 6. Put the 1 in the little box. Drop the 1 down. 1 times 1 is 1. 1 plus 1 is 2. 1 times 2 is 2. Negative 6 plus 2 is negative 4. So we know that this basically divides into x plus 2 minus 4 over x minus 1. This is your oblique asymptote. So actually it should have been closer up here. So that I don't think you have to worry about that at all tomorrow on your homework, but that will come up in a couple of days. Okay, well, I am getting ready to upload this, and I don't know if you can hear music in the background. I'm going to go play Skyrim. Deuces.